Hi everyone, I'm Albert Cheu, and today I'll be talking about separating local and shuffled differential privacy via histograms. This is joint work with Victor Balcer. This talk will hit the following highlights. We'll first go over the definition of differential privacy. It's a constraint on algorithms such that no adversary can learn much about any target. The adversary is computationally unbounded, and I'll specify what it means to learn much. DP is usually in one of two models. Central, where we have a small amount of error, but a large amount of trust. And local, which is the reverse. The newer shuffled model is intuitively somewhere in between the two. In our work, we saw separations between local and shuffled. Specifically, we find that there is a problem which requires many more samples in local than in shuffled. This claim is proven by reduction to histograms. Differential privacy was introduced by Dork, McSherry, and Smith back in 2006. Differential refers to a one-user change in data, which we denote by a tilde between datasets x and x prime. Privacy is, again, a constraint on an algorithm. For any pair of inputs to M that differ on one user, and any output of M, we require that the probability of the event on one input is close to the probability on the other input. Roughly speaking, we want to make it difficult for an adversary to deduce a user's data, but still allow an honest statistician to learn about the population as a whole. The closest is parameterized by epsilon and delta, and we take epsilon to be constant and delta to be much smaller than 1 over n. If epsilon is 0, this is a bound on statistical distance. If delta is 0, epsilon bounds the maximum log likelihood. In the central model, users have raw data and they hand it over to the analyzer. The analyzer's computation is differentially private. In the local model, the analyzer is not trusted with raw user data. Instead, the users send randomized messages. The randomizer R is what satisfies differential privacy. In other words, the privacy barrier is around each user. This is desirable because it addresses the skepticism users might have with large data aggregators. However, there are drawbacks. Work by Bamer et al., Balcer and Smith, Acharya et al., and more have shown that the local model demands larger error and larger sample complexity for the same privacy parameters. Also, Cheu, Smith, and Onion have recently shown that corrupt users can send specially crafted messages to skew estimates and tests. The shuffled model inherits some of the features of the local model. There is again a local randomizer, and there is again an untrusted analyzer. But now there is a service or functionality called the shuffler, which applies a uniform permutation to messages. And it is this big box that must satisfy differential privacy, not the individual randomizers. We simply need to design R in such a way that the output of the shuffler is differentially private. We note that we'll allow users to send more than one message. The shuffler mixes up all messages, so that the first message can be the first message of user 81, and the second message can be the second message of user 27. For the output of the shuffler, the notation we use is S_circ_R, whereas the output of the protocol is the analyzer run on top of S_circ_R. And again, the protocol is private when S_circ_R, the output of the shuffler, is private. The rest of the talk will have two parts. In the first part, we'll describe a histogram protocol in the shuffled model. In the second, we'll give a proof of the separation between the local and shuffled models. In the histogram problem, each user has one of D values. Our protocol outputs D frequency estimates with error independent of D. It uses a special binary sum protocol to compute the estimates. Now, to separate the models, we'll identify a problem where user data are drawn IID. In the shuffle model, it takes just a few samples, but the local model demands many more samples. First, let's put our histogram result in context. Cheu et al. Gave a protocol with error scaling of square root log D and D messages per user. Balcer et al. Reduced the message complexity exponentially. But their error still has a dependence on D. Our work removes the dependence on D. But we have the same communication complexity as Cheu et al. For comparison, a centrally private algorithm has 1 over EPS error instead of 1 over EPS squared error, like we do. But any locally private protocol must have a square log D dependence on dimension. As I said before, we use a binary sum protocol to estimate frequencies. The protocol has 2 special properties. The first is what we call 0 maps to 0. When the sum of the input is 0, the output is 0 with probability 1. The second property is bounded error. The additive error exceeds alpha with probability 1/10 over n. Because of the 0 maps to 0 property, we will take a union bound only over the non-zero frequencies. There are only n of them because there are only n users. So maximum error exceeds alpha with probability 1/10. We'll show how our binary sum protocol works. Each user has a bit that indicates the presence or absence of the element we're counting, and the users release that bit alongside a randomized bit, Bernoulli with mean p. And the shuffler will output a vector of these binary messages. The length of this vector is always 2n. The order is always uniformly random. This means that an adversary can exactly simulate the distribution once we have the sum of the messages. And the sum of the messages is the sum of the user bits plus binomial noise. Our goal now is to find the value of p such that this noisy sum is differentially private. We'll establish some notation. The output of the randomizer is 2 messages, y sub I, 1 and y sub I, 2. The quantity of interest is this double sum over all message bits. For privacy, there is a technical lemma by Balcer et al., which implies that we may choose p very close to 1 if we think of epsilon as a constant and delta as not exponentially small. Below is the visualization of the resulting binomial distribution. Now let's design the analyzer such that we have the 0 maps to 0 property. So the analyzer is the following function. We'll truncate to 0 if the message sum is at most n. Otherwise, we remove the bias introduced by binomial noise. Note that the message sum has maximum value of n plus data sum. So when the data sum is 0, the analyzer will truncate with probability 1. It remains to show that we have bounded error when the data sum is non-zero. Let's first consider a key event. With large probability, binomial noise is only a few standard deviations away from next expectation. In terms of the parameters, this is order square root n times 1 minus p times log n. The log factor comes from the high probability. The remainder of the analysis will condition on this event. Now recall the analyzer has 2 cases. Either we truncate or we subtract NP. If we subtract NP, we'll be removing the bias. Now, given our choice of P, we can show that subtracting NP yields error of 1 over eps times square root log 1 over delta times log n. Because 1 over delta dominates n, the root log factor simplifies to log 1 over delta. Now, if we do truncate, the error is exactly the data sum. But this is actually unlikely for large data sums. Recall that binomial noise is only a few standard deviations away from its expectation. When we plug in our choice of P, we obtain a lower bound of n minus 1 over eps squared times log 1 over delta. So when a data sum is sufficiently large, the message sum will exceed n. So this means, with high probability, the analyzer will only truncate small values, where small is 1 over eps squared log 1 over delta. So returning to our original slide, we have that the maximum error over d estimates is in fact 1 over eps squared times log 1 over delta with 9 times the probability. When I say that the histogram protocol uses a binary sum protocol, I mean that we'll be executing the protocol multiple times, all in parallel. To get a better understanding of what I mean by parallel executions, let's look at how to run two generic protocols at once. You can think of P1 as counting the number of times 1 appears, and P2 the same for 2. Each user will run both randomizers at once. This produces two sets of messages. The users will attach a label to each message that indicates which randomizer produced it. The shuffler will jumble all these messages together. But the analyzer will be able to separate them using the labels. Now that we've established our histogram protocol, let's see what it can do for us. We'll first define the support ID problem. It has parameters h and d, but we'll show that it can be solved with sample complexity independent of d. This comes from our histogram protocol. Next, we'll define the pointer chasing, or PC problem. We'll show that any protocol for support ID, where h equals 2, can be used to solve PC. As a corollary, the shuffled model solves PC with sample complexity independent of L. But Joseph, Mao, and Roth show that the local model requires at least L samples. This means that the local model, lower bound, can be made arbitrarily large while the shuffle model remains small. So what is support ID? We first give some setup notation. H is going to be some subset of the universe 1 through D. For any such H, we'll use use of H to denote the uniform distribution over support H. For example, use of 1, 8 is 1/2 the time and 8 the other half. Okay, here's the problem. Given the size of H and user data drawn from use of H, privately identify the support H. We claim that sample complexity in the shuffle model scales with H log H, but has no dependence on D. Because given this many samples, each element of H will appear at least log 1 over delta over epsilon squared times. Our histogram protocol will estimate the frequencies as positive. Meanwhile, other elements are guaranteed to be 0. This produces a dichotomy from which we can identify H. Now let's go to the pointer chasing problem. In this problem, there are two unknown permutations of the numbers 1 through L. Each user gets one of these two permutations uniformly at random. Here's one example. The goal is to take 2 hops between the permutations. In the example, the value at index 1 is 2, so we need to go to index 2 of the other vector. The value there is 4, which means that we go back to index 4. The answer that we should report is 3. In the shuffle model, it only takes a few samples to identify the support, since it has size 2, the 2 permutations. But in the local model, we require a number of samples scaling with L. This creates this large separation in sample complexity. That concluded our main contributions, but there are still some open research questions. What is the right trade-off between communication complexity and error? Our histogram protocol demanded D messages per user, but can we do better? Also, are there problems that are hard, even ignoring communication complexity? This line of research may separate the shuffled model from the central model. Thank you for watching.